Welcome to the webinar about using simulation to power innovation in life sciences. As the life expectancies grow steadily, people are demanding much more active lifestyles. They're no longer satisfied with medical solution that requires them to cut back on their activities significantly. Picture on the top is a 93-year-old woman taking up skydiving for the first time. Picture on the bottom is the life expectancy for babies born in the US. This presents tremendous opportunities for life science industries with demand for medical devices and treatment that would allow older patients to maintain the active lifestyle they're used to. Rapid process in science and technology such as material sciences, electronics, and mobile technologies enable researchers and engineers to develop more effective, safer, and less invasive medical devices, therapies, and procedures. As the emerging economies keep rising, greater portion of the population can now afford advanced medical cares. Catering to the unique needs of these new market is going to be critical for the success of international as well as domestic medical device manufacturers. To compete in this growing market, companies have to be constantly innovating through in-house research and development, application of the latest academic research, or acquiring technologies from startup companies. With the pressure from competition and the latest healthcare reform, companies are under pressure to be first in the market of new devices to benefit from bigger margin and to continuously reduce the cost of devices while strive to increase device performance. As a tightly regulated industry, faster approval from multiple geographic regions allow the companies to take advantage of the global market. To ensure successful clinical trials and reduce costly recalls, companies need to mitigate these risks during the entire life cycle of the product. All the industry challenges demand for shorter time to market, more competitive products, and lower product costs. Realistic simulation can play a significant role in achieving these goals. To try to understand this, device effectiveness and the device safety, the simulation can help design exploration by changing the material choices and geometries and the manufacturing tolerance. To predict the device durability, reliability, and potential failure, a fatigue and failure analysis can be done for stress concentration and cyclic loading. To reduce the risk of device failure in patients, patient-specific simulation can be implemented by using realistic patient geometries and realistic loading conditions. And all this can be achieved by realistic simulation and durability evaluation to optimize device effectiveness and safety. The SIMULIA has a large footprint in medical device industries with over 100 commercial customers that cover various segments within medical device industry, including but not limited to cardiovascular, orthopedic, drug delivery, vision care, hearing care, surgical equipment, dental, pharmaceutical, medical imaging, and wound management. Today, we're going to talk about Stent design optimization, a show workflow developed for this specific process. Design of a new coronary stents involves consideration of various performance criteria including radial stiffness, durability, crimpability, material and manufacturing choices, among others. As it is time-consuming and expensive to evaluate and optimize a stent design by means of prototyping and physical testing, computer simulations offer powerful techniques to conduct virtual optimization of stent designs early during device development. So in this proof of concept work, a process for optimizing a representative coronary stent model through parametric and non-parametric approaches is demonstrated, and the evolution of design and performance measures of the stent through optimization steps are discussed. So we start with methods about how to create a stent model and perform a stress analysis. Then perform a parametric design optimization in which we can change the geometric properties of the stent such as length of the strut, the width as well as radius of the strut geometry. Then we can also perform, then we're going to talk about non-parametric design optimization in which we're going to show how the the shape of the stent strut itself can be changed through non-parametric design optimization. And finally, we're going to talk about reliability analysis, in which we're going to show how effective the stent is when it is deployed in a range of population in which the size of the coronary artery where the stent is deployed may change from one person to another. So before we go into details of each of those 4 sections I talked about earlier, let's talk briefly about what coronary stent is and how it is deployed in an artery. So a coronary stent is a device to treat a plaque buildup in arteries, and as you can see in this image, it's inserted using a catheter into an artery, and there is a balloon that goes inside the stent, and once the balloon is at this point where the plaque is built up, the balloon is expanded so that the stent expands and it pushes the plaque in and also attaches to the wall of the artery. Once the stent has been deployed or attached to the walls of the artery, balloon is then collapsed and then removed from the artery, and then you finally end up with a deployed stent. And after that, as the blood flows through the arteries, a cyclic loading of blood pressure is applied on the artery as well as the stent over the life of a person. So now we'll go into detail of the stress analysis section and talk about how the model was built for the stent and how the analysis was set up. So we start with creating a 2D sketch of the stent component. So here you will see there is a U-shaped strut and a connector component in here, and all the geometric features of the 2D sketch have been parameterized, such as length of the strut, the radius of the strut, and also thickness. So once we have the 2D sketch, it's repeated multiple times to achieve this 2D shape of the stent, and as you can see, this 2D sketch was made in SolidWorks. So once we have the 2D geometry, it's meshed, and the meshing part was done in Abaqus CAE. So the geometry was created in SolidWorks and then imported into a CAE, and then a 2D mesh is created in Abaqus CAE. That 2D mesh is then extruded, as you can see, along the thickness to generate a 3D mesh, and once we have the 3D mesh of the stent, it's wrapped into a 3D mesh to create a 3D meshed stent part in Abaqus CAE. So once we have the wrapped mesh for the 3D stent, we can proceed with setting up the model analysis. So for the model analysis, there are multiple components. The stent itself was modeled using stainless steel. As you can see on the left hand side is the stress strain graph for the material properties. The arteries is a solid cylinder which was modeled using an isotropic hyperelastic Holzapfel material. On the bottom graph you can see the stress strain curve, and also you can see that the material properties that we have used matches well with the experimental test data that we had for the material properties of the arteries. There are 2 more components in here. That's expansion and the crimping devices, which is a solid cylinder and modeled as a rigid component that expands or contract to implement either crimping of the stent or expanding of the stent. So here's the detail of what stenting deployment analysis includes. So first step is crimping. So once the stent is manufactured, it's crimped, that is, it compressed so that it can fit inside the catheter that I showed earlier, which is inserted into an artery to actually deploy it. But before it can be deployed, it needs to be compressed so that it can fit inside a catheter, so it's smaller. In the next stage is the expansion and the attachment, in which you can see the white component here is the balloon, which expands, and as it comes in contact with the stent component, expands the stent, and then once the stent starts to touch the vessel, it deforms that vessel a little bit and attaches to the artery. On the bottom here you can see the results of the von Mises stress on the stent, and on the right hand side you can see how the blood pressure loading applied and how it results in the stress in the stent. So once the stent is deployed into the artery, the blood starts to flow, and as the cyclic blood pressure is applied onto the internal wall of the arteries, and that pressure is also applied on the stent. And as you can see, the pressure once is start with monotonically build up, and then the pressure is applied into cyclic nature. That also leads to the stress, which is shown in this graph is the maximum stress in the stent. And as you can see, as the pressure increases and decreases, stress also goes through the same cyclic pattern. Because of the cyclic pattern of stress strain in the stent, the fatigue life of the stent can be estimated. The fatigue life is estimated using FE-SAFE tool, for which the material was this 316 stainless steel with ultimate tensile strength. The algorithm used for estimating the fatigue life was Brown-Miller critical plane method, for which Gerber fatigue reserve factor was computed using these equations shown here. And we estimated the infinite life estimate for 2E9 half-life cycles, which is approximately 20 years equivalent. The contour plot on the top right shows the fatigue reserve factor, and the regions highlighted in the red shows the area for which the fatigue factor is the worst. That is, that's a component that is most likely to fail or has this lowest fatigue of lowest life cycle estimate. In this graph we're showing the stress and strain curve for all the nodes or all the elements of the stent. As you can see, the strain is fairly low in the stent, but the stresses are in negative and positive both direction. That means some parts of the stent are in compression and some are in extension, and because of this nature of the stresses in which some are in compression, some are in extension, it leads to the fatigue of the stent. So now we're next going to talk about how to optimize the shape of the stent, that is parameters, geometric parameter of the stent, that is length and the U-shape and the thickness of the stent itself. Let's talk a little more detail about the parametric design optimization. It was done using an Isight design of experiment. Isight is a process automation and optimization tool from SIMULIA, and for this case a design of experiment was conducted or set up in which the parameters for the design of experiments were the length of the strut as shown here, the radius of the strut, and the thickness of the strut which is extruded. The component of the workflow include, we start with modifying the stent model, in which that means modifying the 2D geometry of the stent in SolidWorks, and then from those 2D geometry a 3D mesh is updated in the Abaqus model and a new input file is generated, and then we run the Abaqus analysis and store the maximum stresses that are being generated. So on the right hand side you see the results of the design of experiment. On the y-axis is the maximum von Mises stress in the stent. On the bottom two axis is the strut length that has been changed during the design of experiments, and another axis is the diameter, the outer diameter of the U shape here. Second graph shows the one axis is length again, but the another axis is the part thickness or the extruded thickness of the stent itself. So we want to look at the areas for which the stresses are minimum, and those are the sweet spot for the design. That means if you choose those design parameters, the maximum stress will be minimized in the stent. So the results of the design experiment is that we come up with this design parameters, which is optimized parameters such that the maximum von Mises stress is minimized in the stent. So this is the results of how the shape of the stent looks like after optimization and how the shape has changed. So this is what we started with, the baseline geometry of the stent, and in the green is shown the what's the among all the values that we tested in the design of experiments, this was the most optimized values of those parameters for which the stresses were a minimum. And as you can see in the optimized geometry, the length is slightly larger and the radius is slightly smaller. It's a little more clear when we superimpose the two geometries. You can clearly see here is the length of the optimized stent is slightly longer and the radius is slightly shorter. So what results does it have, and how do you quantify the changes in the performance of the stent after the geometry has been optimized? So in this contour plot, you can see the baseline von Mises stress and some of the areas for which the stress is peak or the maximum stress occurs in those same regions. And because the model is cyclic and symmetric, you'd see the same stress in all the regions of this U shapes of the stent. So after optimization, we notice that the stress has reduced by 5% in those two regions of the stent. Second factor that we want to look at is the fatigue hotspot. So same region where the stress is higher will also lead to the lowest fatigue factor, and those are the two regions for which the fatigue factor is lowest. And the DOE optimized stent leads to 8% improvement in the worst factor. That means the worst factor has improved by 8% in those two regions, from let's say 1.22 to slightly larger value by 8%. So far we talked about how to set up the stress analysis for the stent crimping and deployment. Talked about parametric design optimization, about how to change the geometric features of the stent itself. Now we want to talk about the non-parametric design optimization, in which we change the shape itself of the stent. As you can see, some of the shape of the U part of the stent deforming here, and we can talk about a little more detail of this non-parametric design optimization now. So the non-parametric design optimization was conducted in Tosca structure, in which the design area is specified by picking up the nodes. So we picked up the nodes where we saw the maximum stresses and the maximum fatigue area. For the design optimization, we specify the nodes that we want to deform. So here you can see the highlighted nodes in the red, which are allowed to deform. The objective of this optimization is to minimize the maximum von Mises stress, considering all the load cases, including crimping and the stent deployment, and also the pressure loading of the blood pressure. And the approach is to homogenize the Mises stress distribution so that the maximum stress is reduced. Some geometrical restrictions are applied so that it's manufacturable, and it has a cyclic symmetry, as so far we have zoomed in all the models so far. So here you can see the results of the shape optimization. On the left here, you'd see how the nodes are shifted. So if you focus on this U-shaped region of the stent, you can see some of the nodes shifting inwards, and as you'd see, as the nodes are shifted, the stresses on those, or the fatigue factor in those regions, is also improved. So you can see that in the right hand side, in a slightly better understanding, the curve, how the maximum stresses changes over time over multiple iterations. So we start with 380 maximum stresses in this U-shaped region where you see the red part. You can also see in the contour plot it's red, and as we go over the iterations, in the 6th iteration it's reduced to about 320, and that is about 13% reduction is the maximum von Mises stress. So in the previous step, we talked about how the shape of the stent changed due to parametric optimization of changing the length and the radius of the stent geometry. Now we are showing how the shape optimization results changes the shape. So here you can see that the lines are no longer straight. You can see a little more contour onto the straight part of the stent strut here, and also this little bit deformation in the U part of the strut. And how does it leads to the overall stress and the fatigue factor we have been talking about earlier? So when we did the parametric optimization, it led to 5% reduction in the stress peaks. Doing the shape optimization leads to 14% reduction in the maximum stress or the stress peaks in the same regions that we have been highlighting so far. So that means over the range of 2 steps, parametric optimization leads to 5%, and then when you do the shape optimization or non-parametric optimization, it gives you a further improvement in the stress peaks. We're also going to look at the fatigue hotspot factors. So doing the parametric optimization led to 8% improvement in the worst fatigue factor. Using the shape optimization, now we have reduced it by 14%. So we started with fatigue factor of 1.2, about 1.2 in this region, and now we end up with fatigue factor of 1.41, which is about 40% improvement. So I've shown you these designs in 3D. I also want to show you in 2D how it's a little better to see how the geometry changes in 2D. So we started with this baseline geometry of the stent component, and this is the parametric optimization or design of experiment optimization, for which you can see that the length is slightly longer and the radius is slightly smaller. And once we do the shape optimization, you can see the shape has changed quite a bit. The radial shape is slightly deformed, or then those nodes are slightly pushed inwards, and the straight lines are no longer straight line. You see a little more contour in that region, and since we had applied geometric or cyclic symmetry, you would see those two U curves are very similar. So now that we talked about parametric design and non-parametric design optimization, finally we also want to test the reliability of the stent. And why we want to test the reliability of the stent is because the same stent will be deployed in a range of population for which the size of the arteries might be very different. So that's what we want to test against, that if we change the size of the arteries, how does the performance of the stent changes. So for the reliability analysis, arteries, as I talked about earlier, presents the largest source of uncertainty in the model. So what you're seeing on the right hand side in the red is the artery, how it is modeled using a cylinder. The grayish area is the stent, and the inner circle is the balloon which will be expanded to deploy the stent onto the artery. So to conduct the reliability analysis, there are two parameters that we'll focus on: the inner radius and the outer radius of the artery. By this way we change the shape as well as thickness of the artery. So we are applying 2.5% variation for both the radii. Outer radii we start with a mean of 1.6 millimeter and change by 0.027 millimeter standard deviation. For the inner radius, we start with the radius of 1.132 millimeter and apply the standard deviation of 0.018. So how the reliability analysis is conducted, it's done in using Isight, which is once again a process automation and optimization tool of SIMULIA. The different components included in reliability is you start with pre-processed stent model, by which I mean changing the geometrical parameters of the artery. So changing the inner and outer radius for the range of 2.5% that we have specified earlier. Run the Abaqus model using FESafe, compute the fatigue life cycle. Find out what is the worst life factor is, and then store it for that set of radii values, inner and outer radii values. So this is the response surface. What is the response surface is that it tells you how the fatigue factor changes, the worst fatigue factor changes as we change the inner radius and the outer radius through the 2.5% range, plus and minus. And then once we have the response surface, we use an approximation tool in which and equations are fit onto this surface, so we can do a little more detailed analysis of reliability. So as you can see in this graph, on the y-axis number of points, it tells you how many points belong to what value of the radius for a different combination of the radians that have been tested. As you see, there's a good bell-shaped curve, and the results of the reliability is this. So what you would see is that for a lot of iterations, a lot of points, by each point is a set of one value of inner radian and one value of outer radius. For a lot of those values, the worst fatigue factor does not change. So most of those fatigue factor is in the range of 1.42 of 1.41. So that means for the most of the changes in the radii, the worst fatigue factor does not change. That means the optimized stent geometry that we have come up with is very reliable for a certain changes in the artery dimension. That means it's suitable for different subject to subject variation in the population for the artery size. Okay, to summarize, we started with showing you how to conduct the stress analysis for the crimping and the deployment of the stent. We talked about how the parametric design optimization can be used to improve or reduce the stresses in the stent. The parametric design optimization is used to change the geometric parameter that can be easily changed in the geometry. That can be once you have the initial shape of how the stent should be, such as length, the radius, and the width or the thickness. Then we talked about non-parametric optimization, in which you can even though you have a starting shape, you can make further changes in the shape of the stent to improve the fatigue factor as well as stresses in those certain regions of the stent. And then finally, we talked about the reliability analysis, how to make sure that the optimizer, the new stent design that you have created, is reliable across multiple subject population for which the size and the thickness of the arteries might be different. So here we have shown multiple tools that we have used. So we used Abaqus for the stress analysis calculations, FESAFE for the fatigue factors calculations, SolidWorks for creating the geometry, Isight for doing the parametric optimization as well as non-parametric optimization and automizing those components, and we used Tosca for the structural optimization in the non-parametric design optimization space. So this is the end of the presentation today. Thank you very much for joining this webinar.